All right. Okay, so in today's lab session, well, actually, let's start off with just a quick review. So we've had 2 lab sessions so far. In each lab session, we've gone over how to upload data into SPSS from our local machines. And then we have gone through examples of how to compute summary statistics for a given variable and how to compute QQ plots, box plots, histograms, the general suite of visualization tools that we would consider for continuous data. And last week we talked about structuring one sample or performing a one sample t-test using SPSS output and constructing and interpreting a confidence interval using SPSS output. The first lab assignment is due on Monday at the end of the day, and it's to be submitted via CrowdMark. In this lab session, so after I go through some new material, there should be plenty of time left over for any questions. So if you guys are working through the assignment and you want to ask me some questions about it, I'll be here to answer those. Before we get to that part, I would just like to introduce 2 new topics, which are the independent 2-sample t-test and the paired t-test via SPSS. So to model these 2 types of tests, I've just prepared a little question sheet like I did last class. So questions 1, 2, and 3 are related to the independent 2-sample t-test, and questions 4, 5, and 6 are related to the paired t-test. So for questions for questions 1, 2, and 3, we're going to use the achieve.sav data, which is available on the course website, and I believe we also used this data set last class. And for the paired t-test, we're going to use the typing.sav data, which is also available on the course website. I'll talk a little bit about the differences between the 2 types of tests, but for the most part, the derivation of the test statistics, the discussion on sampling distribution, and the rationale for the different tests will be discussed in lecture. Okay, so starting with the first question, we are going to use the achieve.sav data. So the achieve.sav data, again, is a data set that is comprised of one variable, which is scores. And for the 25 measurements that we have associated with this variable, 13 are female and the remaining 12 are male. So these scores are the score on a math test that was written by the students. So the question that is of interest to us initially, so in part 1 here, is at the 5% significance level, is there evidence of a difference between the average scores obtained by the girls and boys who wrote the math achievement test? So we are interested in comparing the averages of the female scores to the average of the male scores to determine if there's significant evidence of a difference between the 2 population means. All right, so to perform this test, we'll start by checking the assumptions. The first assumption is that we have independent simple random samples. So the description of the data, which isn't given here, but we do have in the lab manual, states that this is in fact a random sample of 25 high school students. Now, on an assignment or a test, obviously a larger description of how the data was collected will be provided, but for the purposes of the example and for the following from what is given in the lab manual, we can assume that the first assumption is met, given that it is stated that this was a random, or that this data was randomly selected. Okay, so assumption met as data was randomly, or as students were randomly selected. Okay, now the second assumption is the normally distributed populations. So to set this up, what we can do is draw a normal probability plot for each gender. So we want to know if the values in for the females, their scores appear to be approximately normal, and if the values for the male students appear to be approximately normal. To draw normal probability plots, we would go analyze, compare descriptive statistics, QQ plots. Now, when we do this, you can see that we can only enter scores into the variable. So one thing that we can do to get around this is we can copy and paste. So I'll select copy with variable names, the values in the first two columns, and then paste them into the second columns. Now what I'm going to do is remove the female values from the second column, or actually it doesn't really matter. I'll remove the female values from the second set and place the male values at the top. And then I will remove the male values from the first set. Okay, so I've broken up the data into 4 components now. So I have the scores for the females and I have the scores for the males. So now when I go analyze descriptive QQ plots, I can select the 2 variables that are of interest to me. So the first one, scores, will be the QQ plot for the female scores, and the second variable, var 0001, this will create a QQ plot for the male scores. Then I click OK. And as I scroll through the output, so here is the QQ plot for the male scores. All right, so I'm going to take this and attach it to my output. So I'm going to screenshot this first one here. And here is the QQ plot for the female scores. Now, I didn't do this with the first one, but I should have. We can also just change the title so that we can show what we are looking at here. All right, and then we can screenshot this as well. All right, and now below here, we can include each of these plots so that we have them for evidence. Okay, and then we can say above here, so when we look at these QQ plots, and I'll just zoom in a bit so that you get a better look at them. When we look at these QQ plots, we can see that the values in each case for the male scores and for the female scores, we can see that the values are pretty close to following the straight line relationship that is shown on the plot. And again, when we are using QQ plots to evaluate the, or to determine if there's evidence for normality, what we would expect to see is that the observed values and the expected normal values are linear with one another. So there is a small deviation here in between the 75 and 80 quadrant, but I wouldn't say that this is a significant derivation from linearity. So I think it's safe to say in each case that the QQ plots are giving sufficient evidence that the variable is normally distributed in each population. So we can write here the QQ plots give or show that the observed quantities form a linear relationship with the expected normal values. This gives evidence that the variable of interest is normally distributed in each for each population. All right. Okay, so now we can actually start to work through the components of the test. So we are interested in testing for a difference between the average scores obtained by the girls and the boys who wrote this, this achievement test. So we are going to have H0, mu1 equals mu2 versus the alternative that mu1 and mu2 are different. So mu1 does not equal mu2. As a reminder, it is also okay to write the hypotheses in the following form. So this here would be an equivalent statement. And sometimes this alternative expression is easier to understand because in the when you're writing these tests out by hand and you're building the test statistic on step 3, you can see where the 0 value in the test statistic comes from. Now, of course, in our context, in the case of SPSS, this isn't such a big deal because we're just getting the output directly. But both of these expressions mean the same thing, and they are both fine in the context of a 2-sample test. Okay, now on step 3, we have to get our test statistic, and we can do this using SPSS. So to do that, we should reconstruct our values as they were originally given. Oh, I think I have, okay, so take this part here. Probably could also just undo, that would work equally well. Oh no, sorry. Oh, maybe I cannot. Okay, I'm just gonna reload it. That'll be the easiest. Okay, so here's the Achieve dataset in its original form. So to compute a 2-sample t-test, we're going to go analyze, compare means, independent samples t-test. Okay, so this will be our choice when we have 2 samples or 2 populations that are independent of one another. Okay, so our test variable is going to be the quantitative variable that we are measuring. So in that case, in this case, scores. And the grouping variable is going to be the variable that differentiates between each of the samples or populations of interest. So you can see that when we're running the independent sample t-test, we have to tell SPSS where to split the data. Now you'll notice inside the grouping variable here, it says define the variables. So we can click on define the variables, and group 1 will be female and group 2 will be male in this case. Okay, so essentially we're just telling SPSS how to differentiate between the scores based off of the indicator in the second column. All right. So then we click OK. And here is our output for the procedure. So we only need what is given in the bottom here. And I'll explain this output momentarily. So now we can insert this image. Okay. All right, so in the output from SPSS for the 2-sample test, you can see that we have 2 rows of information. We have scores equal variances assumed and scores equal variances not assumed. In our particular illustration, we are going to be focusing on the output from the equal variances not assumed column. So the test that we studied in lecture and the test that we are following through with here in the lab is the test based off of the assumption that the variances are not equal. So our output is going to focus on the second column, second row. Now, if you have learned about the pooled or heard of the pooled 2-sample t-test before, the first row of output is the output from the pooled version of the independent 2-sample t-test. But again, we're studying the non-pooled procedure. So our output was going to correspond to the second row. So with that being said, our test statistic here is going to be 2.078. All right, now in step 4, our p-value is going to be 0.051. And as a reminder, the p-values that are given in SPSS are the 2-tailed p-values. So if we're performing a 2-sided test, like we are in this particular example, then the p-value we can take directly from the output. Okay, so now on step 5, we can conclude, so we do not reject H0 in this case, because our p-value is larger than alpha. Since p-value is greater than alpha. And then on step 6, we conclude by saying at the 5% significance level, the data do not provide sufficient evidence to suggest that there is a difference in the population mean scores achieved by girls and boys, by the girls and boys who wrote this math test. I can just move this up a little bit. Okay, so there is a complete solution to problem 1, which again is a 2-sided hypothesis test comparing the mean score for the females against the mean score for the males on this math achievement test. Okay, so to run the test in SPSS, so do you guys have the columns that show, do you have the little red, blue, yellow symbol here in the second column for the grouping variable?
Yes.
Oh, sorry. Okay, so we're gonna go analyze, compare means, independent samples t-test, right? And then these 2 variables would be on the outside here. So scores inside the test variable, and then sex inside the grouping variable. And then we click define groups. And then for group 1, I type a capital F. And for group 2, I type a capital M. Does that work? Sorry, I didn't mean to mute you there. I thought it was an accident.
No worries. I think it's because I typed the word female in male. That's probably why it didn't work.
Okay. Yeah, I think the symbol has to match what's given in the. Okay, cool. So then continue, and then okay, and then the output should be included. You guys have
Yeah,
that?
it did work on me. Thank you.
Nice. You got that, Sam? Can I call you Sam? Cool. All right. Right. So again, from the output, we're going to focus on the second row because we're doing the test that does not assume equal variance. And then following from the output, we have our test statistic, we have our p-value. Again, the p-values from SPSS are always two-tailed p-values. So in this case, we don't have to divide by 2. And then we can say we do not reject since our p-value is bigger than alpha. And then at the 5% significance level, we do not provide, or the data do not provide sufficient evidence to suggest there's a difference. Okay. Does anyone have any questions regarding the hypothesis test? Okay. If not, then I'll move on to question 2. So in question 2, we want to calculate and interpret a 95% confidence interval for the true mean difference in scores between the boys and the girls who wrote the math achievement test. So you can actually see in the output for the 2 sample test, we're given the 95% confidence interval directly. Now, just for completeness, when we select independent samples t-test, you can see that after we set up the test variable and the grouping variable, we have an options category here. So inside the options category is where we can select the percent confidence level. So for example, if we had wanted to compute a 90% CI, we would make the change inside options. If we wanted to compute a 99% CI, we would make that change here as well. The 95% CI is the default. So technically we didn't actually have to make this change, but if on the assignment you're asked to compute, a confidence interval that isn't the default, so not 95%, you would do that by setting up the independent samples t-test, clicking options, and inputting the confidence level. Okay, and then when you click OK, you're going to get the same output that we already had for this particular problem. All right, so for step 1, we're going to give the confidence interval. So we'll use the same output that was given above. So the 95% CI is negative 0.030 to 16.119. And then on step 2, we can say we are 95% confident that the true mean difference in scores on the math achievement test between girls and boys is between negative 0.303 and 16.119. Right. So again, the nice thing about computer software and the way that SPSS in particular does its hypothesis testing is it generates our confidence intervals for us automatically. So we're able to produce the test result and the interval in the same format, which makes handling questions like this a little bit easier and a little bit quicker because we have everything in one piece of output. Okay, any questions about the confidence interval construction? Okay, in question 3, it asks, do the results from 1 and 2 agree? So these are interesting questions in the context of comparing a hypothesis test to a confidence interval. So in 1, we tested the following. So in question 1, we tested the following hypotheses. The data gave no evidence to reject H0. Right? So what this means is, okay, so this means that there's no evidence that the average scores for the girls differs from the average score for the boys. Okay, so basically what we're saying here is there's nothing that suggests mu1 and mu2 are not the same value. So they're equivalent. So their difference would be 0. In 2, we found a 95% CI with the following limits. So what we can notice here, notice that the 95% CI contains 0. Okay, so this is the big part of it. When we're evaluating the relationship between a hypothesis test and a confidence interval, the main way that we evaluate is by looking at the confidence interval and saying, does the interval include 0 or does the interval not include 0? Since the interval includes 0, this means that a possible value for the difference between mu1 and mu2 is 0. This suggests that a possible value for the difference between mu1 and mu2 is 0. This agrees with the conclusion we found in 1. Okay, so in general, or to summarize, since the CI contains 0 and we found no evidence to reject H0, the hypothesis test and confidence interval give the same conclusion, i.e., that is, they agree. Okay. So when we're asking, does the confidence interval agree with a hypothesis test, or do the confidence interval and hypothesis test give the same result? Effectively, what we're asking is, if you did not reject the test, does the confidence interval include 0? And if you did reject the null hypothesis, does the confidence interval not include 0? So that's what we would be looking out for when we're comparing the CI and the hypothesis test. Any questions regarding that idea? Okay, so in questions 4, 5, and 6, we're going to take a look at how to perform a paired t-test in SPSS. The paired t-test is our 2-sample t-test that is used, or that we use when the samples of data that we are working with are not independent. So we distinguish between the independent 2-sample t-test and the paired t-test based off of the structure of the data and how the data was collected. So to illustrate a paired data set, we are going to use the typing.sav data. Okay, so we're going to load the typing.sav data, which is available on the course website. Okay. And when you load this data set, you should only have the before and after variable. Okay, so what is the structure of this data set? Well, the before variable contains scores achieved by persons that took a typing exam. So it's sort of like a score that assesses your rate of speed slash number of mistakes when you're typing. The after variable represents your scores for assessing that same ability after you took a typing course. Each of the 8 observations in the data set represent 8 different people that took this course. So in this particular example, we have a typing score for each person before they took the course and a typing score for each person after they took the course. This creates paired data because the variable before and after are not independent of one another because each value is measured on the same person. So the most natural example of paired data are examples like this, where each observation in the data set is contributing 2 measurements. So we cannot assume that a person's score after they took the test is independent of their score before they took the test because it's the same individual taking the test. So any natural sort of inclination towards typing or lack thereof would be consistent across both measurements. All right, but we still would like to answer general questions about the mean difference and compute confidence intervals to estimate the true mean difference. In particular, we're interested in determining if at the 5% significance level, the data provides sufficient evidence to suggest that there is an increase in typing score after the students attended a typing course. So we would like to know, is there evidence that the values in after are greater than the values in before? Okay, so to set this up, we're going to have a very similar setup to what we had before. So I'm just going to pull some of the information from above. So we'll start off with our assumptions here, and then we'll have our hypothesis test. Okay. So when we are working with a paired t-test, we operate on a variable that is called the differences. So we usually write our assumptions as simple random sample of differences, normally distributed population of differences. Okay, and then in this case, our null and alternative hypotheses, we can write these as mu1 greater than mu2. So we should write, for clarity above here, declarations. Sorry. So let population 1 be the scores after the test, and let population 2 be the scores before the test. Okay. All right, so we're going to have mu1 is greater than mu2 because we're asking if the scores have increased after they wrote the test. So that would imply that mu1 exceeds mu2 after they wrote the test. And then our null hypothesis, of course, is just going to be the opposing symbol, which is less than or equal to the mu1 less than or equal to mu2. Where is that thing? There's this direction. Here it is. Okay. And usually, when we're working with paired data and we're structuring our hypothesis test, we actually build it around the symbol mu d. So this hypothesis, as it's written here, where we're comparing the 2 population means, this actually is okay because it is asking the same question. but typically we write paired hypotheses as follows. So we would have, in the place of mu1, we will have mu d, and then this will be less than or equal to 0 now. Mu d here greater than 0. And this is most likely how you're going to see it in lecture example, and how I think this is how most students would write it when working through assignments and whatnot anyways. But technically, these two expressions are the same thing, but usually we phrase our paired t-tests around the variable mu d, which is the mean of the differences. And that aligns with what is given in the assumptions that are written above. Okay, so the first assumption is the simple random sample assumption. So let's just, in this case, what we're referring to are the observations themselves. So were the observations that were collected, so the 8 people that took the course, were they randomly selected? Okay. So in the lab manual, there isn't really any indication as to whether or not it's a randomly selected sample. So we're not actually sure based on description if this is true. So we'll have to address this a bit later, but we'll continue to work through the test and then we'll make a note of this later on. Okay, the second assumption is normality of the differences. So what we're going to do here is first, we're going to compute our differences. To compute the differences in SPSS, we click transform, and then we go to compute variable. Okay, so transform, compute variable. Then we give the variable we are creating a name. So we can just call this diff for differences, but you can call it differences if you want to, that's fine. Now we have to select the direction in which we are going to compute the differences. So we want to test that the score after they took the test, after they went through the course, is greater than the score before they went through the course. So the natural direction to take here would be after minus before. So we're going to take the scores in the after variable and subtract the scores in the before variable. Okay, so again, we go transform, compute variable. The target variable is our name for the differences. And then we select the order in which we want to upload those values. So after, and then we click minus, and then we upload before. Click OK. And then you can see that what SPSS does is it places the differences into a new column. So to check the normality assumption of the differences, we can make a QQ plot of these difference values directly. So we would go analyze, descriptive, QQ plots, and then we would just select the differences. Right? So essentially this is basically just a one sample t-test, but we're operating on this difference variable rather than on the before and after variables. Rather than on the before or after variables. Okay, so here's our QQ plot of the differences. So we can take this here and we can upload it into our Word document. This might be a little bit big. All right, and then I'll just move this stuff down onto a new page so that we can get it all together. Okay, so here's our QQ plot. All right, so same idea as before. All we're really looking for here is evidence of linearity between the observed differences and the expected normal values. So we can say here the QQ plot shows that the observed differences are linear with the expected normal values. This gives evidence that the population of differences is normally distributed. All right. Okay, so the next thing that we have to do is actually follow through on the rest of the test. So as a reminder, we have our null and alternative hypotheses set up. We're asking if the scores after the course are greater than the scores before the course. So we have an upper tail test here because we declared the first population to be the scores. And when we computed our differences, we did after minus before. On step 2, we have our significance level. And now in step 3, we need to get our output for the t-test. So we can actually do this in 2 ways. The direct way would be analyze, compare means, paired samples t-test. That's what we're performing, so it makes sense that we would use this approach. So paired samples t-test. In variable 1, we're going to enter after, and in variable 2, we're going to enter before. So when we use the paired samples t-test command, variable 1 represents the leading variable, and variable 2 represents the variable that's going to be subtracted. So to be consistent with our difference calculation, we do after minus before, or we do after and then we do before. All right, and then we click OK. Okay, so here's our paired sample output. So we're going to insert pictures from file. Okay, and then here is our paired sample output. All right, now, just like before, everything else pretty much falls out from what we've already studied. So we can see that t is equal to 2.807 based off the output. On step 4, our p-value is going to be 0.026 over 2, which is 0.013. So again, SPSS always gives us 2-tailed p-values. So if we want to get the upper tail p-value in this case, we have to divide the output value by 2. And now on S5, we can say reject H subscript 0 since p-value is less than alpha. Right. And then on step 6, we can say if the SRS assumption can be verified, then the data give sufficient evidence to suggest that the population mean typing score after the course exceeds the population mean typing score before the course at the 5% significance level. So for the most part, it's a pretty standard approach. You can see that the way that our tests are being structured, is the same as it was before. And the way that we read the SPSS output is also the same as it was before. Again, on step 4 here, we're making a compensation because the p-value is the 2-tailed p-value in the output, and we want the 1-tailed p-value because of the structure of our test. All right, in question 5, we want to compute a 90% CI for the true mean. All right, so here, okay, so here we're going to go analyze, compare means, paired samples t-test. And in the options category, we're just going to change our confidence interval percentage to 90. So this is the same idea as with the independent sample t-test and as with the one sample t-test. So to select the confidence levels, once you have set the test up, you click option and then you input the level that you want. So in this case, 90%, we click OK. And you can see here that the output for the hypothesis test is the same as it was before. But the output for the confidence interval has now changed compared to question 4 because we have changed the confidence level. So the 90% CI is 3.21083 to 16.53917. Okay, so then we can say at the 90% confidence, or we are 90% confident, sorry, that the population mean difference between the typing scores before and after the course is between 3.21 and 16.54. Okay. So again, should be fairly consistent with what we saw above. Now, I want to point out something interesting here. I'll just answer question 6 or work through question 6 first, and then I'll go back to this point. So question 6 is the same question as what we saw in question 3. So we're comparing the hypothesis test output to the confidence interval. So in 4, we rejected the null hypothesis of no difference. So in question 4, we said we can reject H naught to conclude that there is evidence that the mean typing score after the course is greater than the mean typing score before the course. Okay, so this suggests that the mean difference is larger than 0. Okay. Well, this suggests that the true mean difference is larger than 0. Okay, the 90% confidence interval gives 2 positive bounds. So this, first of all, the CI does not contain 0. This also suggests there is a difference. Second, the CI is giving evidence that the population mean difference is between, well, as we wrote above, 3.21 and 16.54. That is, the CI suggests the difference is greater than 0. Okay, so therefore, the hypothesis test and CI agree. So the confidence interval here is again matching the result of the hypothesis test. The hypothesis test has given us evidence that the mean difference is larger than 0. The confidence interval has 2 positive bounds, which means that it is also suggesting that there is a difference because 0 is not included in the interval. And furthermore, that the difference is a positive value because everything inside this confidence interval range is greater than 0. So again, the two methods agree with each other and give the same conclusion. Any questions so far regarding what we have just worked through with the paired test? Right. I want to show you guys one more thing before I stop with the teaching material for today. So I had mentioned briefly that a paired test is actually just a one sample t-test. So to show that this is true, if we consider our data set, so we have this column of differences. If we select analyze, compare means, one sample t-test, and we submit to the one sample t-test the differences, and then we compute the 90% CI again. Okay, so instead of using the paired output, so when I go analyze, compare means, Instead of selecting paired samples, which is fine, I select one sample, but I submit the differences directly. If I do this and I inspect the output, you can see here that the output for this test actually matches exactly the output for the paired sample t-test above. Okay, so consider the one sample t-test output applied to the differences. So check that out. You can see our t-value here, 2.87, is the same as the paired t-value. Our p-value here, 0.026, is the same as the p-value. And the confidence interval, 3.21 to 16.539, is the same as that given in the paired sample output. So what a paired t-test really is just a one sample t-test, but applied to the difference variable directly. And we can get at that in two different ways using SPSS, through the paired sample selection or through the one sample t-test selection. Okay. All right. So if there's no questions, I will stop with the teaching material at this point. So I'll stop recording the lecture and post what I have up till now. And then for the remaining time, if anyone has any questions about this material or about the first lab assignment or about any of the other concepts in the course, I'll be happy to answer those as best I can. And if not, have a good weekend, and I'll talk to you guys next Friday. And keep in mind that lab assignment 1 is due Monday. And in terms of your lecture material, you should have an assignment due next Friday and probably a quiz due next Friday, or a quiz in class next Friday as well. All right, so as I said, if you're hanging around, I'll be here. Otherwise, take care. Okay. Sorry, one sec. I just need to